Hi, today we're going to talk about rational numbers. First, let's discuss a definition of what a rational number is. And it's any number that can be written as a quotient. Quotient means a division problem in the form a over b. So a is the numerator, b is the denominator. However, there's a restriction on this. The denominator b cannot equal 0. So rational numbers, any number you can write as a quotient in the form a over b. Here's the fraction where this is anything but 0. All right, so let's take a look at our sets of numbers. There's actually another set here, which is our counting numbers, which would go really even right there. Because if I asked you to count, you would probably start off with 1, 2, 3. Those are your natural numbers or counting numbers. The next set we have is our set of whole numbers. The whole numbers include 0. That's the difference between your natural numbers and your whole numbers. From there, we include our negative numbers, -1. So these are our positive numbers, including 0. Then when we include our negative numbers, -1, -2, -3, going in the opposite direction of 0, that's our set of integers. So we have our whole numbers, then that is inside the whole set of integers, which includes our negative numbers. And both of these sets are inside the set of rational numbers. So let's take a look here at an integer. Well, first, a whole number, 75, that's an example. 3 over 3 is 1. Okay, these are all my positive numbers and 0. -1. -1 divided by 1, -7 divided by 1 is -7. Integer. -12 divided by 6, -2. Integer. And -130. Those are my negative numbers. Now, over here, we have the fraction 6/7. -3/4. Even a repeating decimal is a rational number, and we'll learn how to do that. -4 7/8, and I showed you here because this is written as a fraction, a over b. It's an improper fraction. Likewise, the decimal 25/100ths can be written as the fraction 25 over 100, and -7 over 2, even though it's an improper fraction, it is still written in the form a over b, where b does not equal 0. So that is probably one of the most important definitions that you have to learn. Now, let's take a look at the first example. Write 2 lists of fractions equivalent to 1/2. There is an infinite number of fractions that would be equivalent to 1/2. Let's take a look at a couple of them. Well, I have 1/2, 2/4, 3/6, ... The numerator and the denominator are both positive. Now, there's another way of looking at this. I could have 1/2, and I could look at it -1 over -2. It's still positive. Negative divided by negative is a positive. And -2 over -4. So let's try a couple. Number 1, I have 1/3. Well, I want to write this. How could I do this? Well, I could say multiply numerator and denominator by 2. That gives me 2/6. I could also say -1 over -3. I could also say -2 over -6. So negatives, both of them also would simplify to 1/3. What about number 2, -4/5? Well, I could say, if I multiply them both by 2, -8 over 10. Now here's where it gets a little bit tricky. I can take that negative and put it down here. Okay, because technically what I'm doing is multiplying them both by -1, which would make that positive and that negative. I could also make this that. Look at number 3. 5/8, well, of course, 10/16. I could also say -5 over -8. I could also say -10 over -16. I could say 50 over 80, -50 over -80. What about number 4, -1/2? Well, obviously, -2 over 4. I could say 2 over -4. I could say 1 over -2. Pretty easy. They are all equivalent fractions, just a little bit different than what we're used to. Look at example 2, graph each rational number on a number line. Well, if you take a look at what I've done here, all of these are between 1 and -1. So I made my number line only between 1 and -1. It gives me a little bit more room here. All right, and then I like to locate where's my halfway point. So I have 1/2 is between 0 and 1, and -1/2 is between 0 and -1. Now I'm going to plot these. Well, 1/2 obviously is right here. That's the letter A. And then I have -8/10. So if you want to think about that, break it up into 10 parts. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's where -8/10 would fall. 1 is over there, letter C, and -2/10 would be right there. So let's try a couple. -1/2. Now, notice here, I'm going all the way up to -2. So I'm going to keep it even on both sides. So 0, -1, -2, and 1 and +2. So I'm going to look at the first one, number 5. -1/2 would be located between these two right here. All right, so that would be a -1/2. That's number 5. -4/10. Well, again, I'm going to break this up into 10 pieces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So -4/10 would be right there. -2 is right there. That's number 7. This was number 6. And -9 or +9/10 would be again 1, 2, 3, 4, 5, 6, 7, 8, 9. And a +9/10 would be right there. Okay. All right, look at example 3. The speed of a car changes from 37 feet per second to 102 feet per second in 5 seconds. Your speed is getting faster on the car. What is its acceleration in feet per second squared? That's the abbreviation, feet per second squared. Use the formula, acceleration equals F minus I divided by T. A is acceleration, F is your final speed, where do you end up? I is your initial speed, and T is the time it takes you to get there. So now we're going to just substitute in what we know. Our final speed, we're going from this initial to this. So 102 is my final, 37 is my initial in 5 seconds. 102 minus 37 is 65 over 5 means you're accelerating at 13 feet per second squared. And finally, let's try a couple. Evaluate each expression for A equals 6, B equals -5. Look at number 9. A equals 6, B is -5 over -3. 6 plus -5 is 1 over -3, or we could say -1/3. We usually write that with the negative into the numerator. Number 10, 7 minus B, which is -5. Be careful of that double negative there, over 3 times 6. 7 minus a -5 is the same as 7 plus a +5, which is 12 over 3 times 6 is 18. And now we can divide both of those by 6 to simplify, and we get 2/3. And finally, the last one, A plus 9 over B. A is 6 plus 9 over B, which is -5. And 6 plus 9 is 15 over -5, which is -3. And that's it. Good luck.